Hi, in this video, I'm going to introduce some basics of simple linear regression. This is the scatter plot that displays the positive association between GDP and carbon dioxide emission from 10 countries you saw previously. As you can see, this 10 points seems to fall along an invisible straight line. The red line here is the best fitting line that can describe the linear relationship between the two variables. This line can also help predict the value of a dependent variable when a value of the independent variable is given. A straight line in algebra can be expressed by y is equal to b0 plus b1 times x. b0 is the intercept, which shows the value of y when x is 0, and b1 is the slope, which shows the change in y when there is 1 unit change in x. Statisticians find this best fitting line using the least squares algorithm that minimizes the overall vertical distance of data points from the line. So the best fitting line is also known as the least squares regression line. To find this line, you can get its slope by multiplying the correlation coefficient by the ratio of the standard deviation of y to the standard deviation of x. Once you get the slope, you can use it with means of x and y to obtain the intercept. In the GDP and CO2 dataset, the intercept is 102.32 and the slope is 196.18, meaning that when GDP increases by $1 trillion, CO2 emission increases 196.18 million metric tons. Keep in mind that you cannot extrapolate from the regression line too far outside the range of the observed data. It is because the data points outside the range may show a different pattern from the existing data. Unless you have a perfect linear relationship, in real world, not every data point falls exactly on the straight line. The vertical distance of a point from a line is called residual, EI, and here is the residual of the 10th data point. Some points are above the line while other points are below the line, so they are positive and negative residuals. To measure the overall distance, we square each residual to get positive values only. If you then sum up these positive values, you get residual sum of squares, shown as SS of residual. In fact, the least squares regression line is defined by minimizing this quantity. If you divide residual sum of squares by n minus 2, then take the square root, you get residual standard deviation. This quantity measures the average variability of the y values about the least squares regression line. The square of residual standard deviation gives you residual variance. Not all values in y are the same. Some are lower and some are higher, and the up and down feature or its variation can be measured by variance. You can think of variance as an average distance of each value from its mean. When you fit your data with the linear regression line, the total variation of y, or the dependent variable, can be partitioned into two parts: the variation explained by the linear regression line and the variation that cannot be explained. Here is the equation to show this idea. If you move the unexplained variation to the left side of the equation, divide the left side by total variation, you get the proportion of the variation explained by the linear relationship in relation to the total variation. This explained variance can be approximated by coefficient of determination, denoted to R squared, which is the square of correlation coefficient. This approximation is the best when there are many pairs of data. Based on its definition, coefficient of determination is always between 0 and 1. When it's 1, it means all variation in y is explained by the linear relationship. When it's 0, none of it can be explained by the linear relationship. Here is another example. The scatter plot shows the height and the peak flow rate of 15 men. The peak flow rate is an indicator of respiratory health, which is the fastest rate when a person can expel air after taking a deep breath. Researchers wanted to know if there is a relationship between the height and the peak flow rate. They made the scatter plot and found the least squares regression line that the peak flow is determined by 6.78 times height minus 588.1. And the correlation coefficient from their calculation is 0.53. How to find the predictive peak flow rate for each subject, the residual, and the proportion of the variation that is explained by its relationship with height. Let's look at the first subject. To find its predicted peak flow rate, you just need to plug its height to the equation and you end up getting 591.36. Similarly, you can get other predicted values by using their corresponding height. Residual is the difference between the observed value and the predicted value. So the first residual is 733 minus 591.36, and you get 141.64. And if you subtract every predicted value from its observed value for each subject, you get residuals in the last column. An easy way to answer the third question is simply to take the square of the correlation coefficient. Based on this, the proportion of the variation in peak flow rate that is explained by the linear relationship is 0.28. Apparently, the majority of the variations in the peak flow rate is captured by other factors. To echo the key points in this video, you've learned how to find a least squares regression line and use it to make a prediction of a dependent variable when a value of the dependent variable is given. There are quantities to measure the distance of predicted values from observed values. And you also learn the coefficient of determination. That is a very useful measure of the performance of this regression on capturing the variation in the dependent variable.